Thank you so much for having me. I'm Steve. I would like to share with you some basic information about Rust, which is I'm lucky enough to have a day job that involves working on open source. So this has been what I spend most of my time on nowadays. Historically, if you're not familiar with my previous work, I have worked on Rails. I have a Ruby tattooed on my body, so I was kind of into it a lot. I also have a Perl camel, though, because you can't just have one scripting language tattoo. You need at least multiples. And so now I'm doing Rust stuff. So a little bit of meta stuff. What is Rust, if you're not familiar? Rust is a brand new programming language from Mozilla and friends, other people. Although it's funny, when you're working on a pre-release programming language, most of the people that work on it are either working for Mozilla or are students or put in a lot of weekend and night hours. So we do have core members that are not from Mozilla, but the vast majority of people are Mozillans. Rust is a little hard to talk about, and we've sort of been evolving the marketing for Rust because it's interesting. So Rust is a low-level programming language, but it often feels like a high-level programming language. And so it's sort of awkward. It's not trying to be everything to everyone. It's just that when you take modern programming language features and you bolt them onto a low-level language, a lot of times you get something that feels more high-end, even if it is not. So it's hard to describe how Rust gives you the low-level power that C and C++ do while feeling high-level like a Ruby or Python or ML. And so you don't want to alienate the low-level people by saying no, seriously, you can have your pointers and your low-level memory management, but you also want to tell the high-level people, don't worry, you don't have to worry about that stuff. So it's a little awkward. So I hope to show you what I mean over the course of this talk. And I think what makes Rust really special is that it makes low-level programming accessible to people who have not done low-level programming before, and it makes it safer for people who do have experience with this low-level stuff. And I'm going to spend most of this talk talking about what I mean exactly by safety, but basically what it boils down to is historically, this is a slide from the most recent Apple keynote, and I think that lots of programmers think about programming languages just like this chart, actually. So you tend to think that there's this line, there's a trade-off, right? Programming is largely an engineering discipline, or at least it feels like it. And so we tend to think about things as trade-offs. So one of the big trade-offs in programming language design, and when you choose what language you want to use, is that there's this performance axis on one side and a productivity axis on the other. So you tend to think of languages like C and C++ as being incredibly low-level and therefore not productive, because you really, really need to be careful to pay attention to dot all your I's and cross all your T's and asterisk all your pointers. But in exchange for that tedium, you get unparalleled performance, right? So there's sort of this when you let people interact with the system as low as possible, you can get, you make the computer do exactly what you want it to do, and therefore you get performance. If you pick a language like Ruby or Lua or Python or JavaScript, you get this productivity of not needing to worry about things like memory allocation, but the downside is you end up spending 300 megabytes a server on your Rails process, right? And so this is sort of the way that we tend to think about things. If you want high performance, you're going to have to involve danger. If you don't want high performance, then you get all these nice tools. And there's a couple of languages that are coming out in this space, and I think Swift does a decent job of being like this too, which is why this slide makes sense. But we're finding out increasingly with new programming language stuff, you actually don't need to sacrifice performance to gain productivity. And in fact, some of that is due to programming language theory. Some of that is just due to things like tooling. So I'm going to talk a lot about tooling towards the end as well. But we've sort of been able to import a lot of the lessons that we've learned from high-level stuff back into these low-level languages. I've been programming for almost my entire life. I started off with GW Basic and then learned C. So sort of my own personal progression has been doing low-level things and then moving into high-level land. And now I'm sort of going back into low-level again. So a lot of the stuff is that's my perspective because that was also my personal journey with programming. But I think also just as an industry things move. But I think that this might be the wrong way to think about programming languages because this doesn't actually have time involved, right? So for example, JavaScript used to be incredibly slow and now is quite fast. So how does that play into a chart like this? Does it move along these axes? So I'm not totally sure this is the best way to characterize languages, but it's definitely a way that we tend to think about them. Okay, I'm going to make these slides go a little smaller again. So safety, when I talk about safety, what do I mean? And this is really important in the context of Rust because Rust says that it is a safe programming language, but it means this in a very specific form. It means memory safety. So low-level programming has historically been very, 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 very unsafe. Let me show you what I mean. Here's some Ruby code. Oh, also, I should mention this too. So my slides are kind of interesting. We have a tool that documents like API documentation in Rust called RustDoc, and it can also process regular old Markdown files. And so last week, someone wrote a thing that injects the right HTML and CSS to give you slides in RustDoc. So these slides are actually generated by Rust code generating HTML. So the styling is a little awkward because it's not totally done yet. And it only uses features that are implemented in Servo, which is the browser engine that they're writing in Rust. And so, unfortunately, Software Freedom hates me today, and so I'm borrowing my friend Chris's laptop. So I was going to show you like Servo running my slides in stuff, but oh well. That's what I get for using Linux. Can't present on anything. So I'm going to scroll down a little bit for some of these slides. But here's some Ruby code, and this is a little, made up, but it illustrates my point. So we create an array called v, we push an element onto that array, then we set a variable x that's a reference to the first element of the array, we then push world on and we put x. Now, because Ruby is memory safe via its garbage collector, this will work, and it will print out hello, actually, if I remember correctly. But like the world does not break down, everything works, it's fine, it runs. If you write this same code in C++, it's a little bit longer, but it pretty much looks like the same thing with a little bit more type annotations. So you have int main, we create a vector, and we have to say that it's going to be a vector of strings. We call it v. Pushback is the method on vectors that's the same as push in Ruby. So we push a hello. Then we take a reference to the string that is at the first element of the array, and we call world, and then we print out the value of x. I don't know how many people are like experienced C++ programmers in the room, but like, and this is also the most set up question ever, right? But like, do you think that this works? No. Someday I'm going to make a slide that's like going to have that be a thing. Small tangent, I've joked that if I ever write a science fiction trilogy, I want it to be like set up in the first episode, and then the big battle in the second episode, like modeled after Star Wars, but then the bad guys win and there's no trilogy. But you just like tell everyone it's going to be a trilogy. So that's the problem with trilogies, is you always know that no matter what predicament they get in the second movie or book, it's never going to be bad. Someday I'll do that with slides. But no, so this doesn't actually work with G++. So if I say, if I turn on all warnings and I make them errors, and actually, now that I'm looking at this, I think that WAll is actually not all warnings anymore. I think there's also an extended, or whatever it's called, versioning. But this code will give you no errors whatsoever, and then when you run it, the slide says it's seg faults, and it does on my machine. But what's fun about this code is it's actually undefined behavior, so like anything could actually happen. Some machines, like I had some people run this on OS 10, and it will not seg fault, it will work. But on my Linux machine, it will break, and I didn't try it on Windows because I don't even know how that works at all. So why is this undefined behavior in C++, and why does this like work properly in Ruby? So let's go over this code a little bit, and I'm going to have some scary hex numbers for memory, but like if you haven't dealt with low-level memory stuff in a long time, you just know there's memory locations and they have a hex address, and then I'm going to show the name that we put in C++, and then the value that's stored at that location in memory below this code. So we say, okay, I want a vector, and it's going to have some strings in it. So we get an address, 0x30, and it's going to have v. And then when I call pushback hello, it allocates another element to the array, and it stores the string hello there. So we have our v, and it points at this location. When we make the reference to that string at v0, we now get a pointer. So this reference / pointer is at the address 0x14. The value of that pointer is 0x18 because it's pointing at the first element of the array, the hello, right? Here's the tricky bit. So when we then push world onto the array, we only had an array of length 1. And if you'll notice, like back here, the hello and then the pointer being right after it, there's no room to place that second element of the array. So we have to allocate a new set of memory and copy the first value over into that new memory to make room for the fact that this array has grown in size. And so when you do that, the value that was at the old place the array was located at, 0x18, is now a garbage value, and you can't trust what's there because it's not correct. And the vector in the standard library will handle updating the original reference. You notice that the v is now pointing at 0x08, which is still pointing at the beginning of the array. So that pointer has been changed appropriately. But our x is now dangling. It points at 0x18, which is undefined garbage memory. And so this is what happens, and this is why when you run it and you try to print out this garbage memory, everything just blows up or doesn't, question mark. And what's fun is that like basically C++'s answer to this kind of problem is, well, the documentation says if the new size is greater than the capacity, then all iterators and references are invalidated, so don't do that. But there's no ability of the tooling in the actual language to handle this kind of thing. And this isn't because the people that write C++ are dumb. It's because they've been building up you know, a long amount of backwards compatibility, which is one thing that's really nice. I think one of the things that I am sad about in my Ruby days is how little Rubyists care about backwards compatibility. It seems like if I deploy a Rails app this week, like 6 months from now, I don't know if it's going to still work or not because I haven't been like updating all the things all the time. So backwards compatibility is nice, but because the heritage of C++ is so old, they can't actually fix these kinds of problems at the language level anyway, without introducing backwards incompatibilities, which they don't want to do. So this is where we're at in the like C kind of era. And because systems programming is very hard, and because less and less people are writing in low-level programming languages, this has kind of been the status quo for a long time. These are the sharp edges that happen. And in a program like this, you have to remember the error message that you get is segfault, right? And you can do some stuff with that core dump, but like, if this was a big, giant program, like imagine if this is 1 million lines of code, right? Now you have to figure out what segfaulted and where and why, and it might be this huge, like, complicated situation. And it's just really hard to debug, and you have to be perfect. And I don't know about you, but I am a bad programmer, and I am fallible, and I will screw things up even if I know the right answers. And so let's talk about what happens with this in Rust. So I'm not going to give you the like super details about Rust syntax in this particular iteration of the talk. You are programmers. You can pick up what a vector looks like and what array accesses look like. It looks vaguely familiar. There might be a little bit of weirdness, but I'm just going to show you. So here's function main. We make a mutable vector that is empty. Because in Rust you need to annotate things that are mutable, things are immutable by default. We push the hello onto there. We make a reference to that first element. We push a world on there, and then we try to print out the value of x. So again, super loaded question, does this work or not? The answer in Rust is it actually does not compile. So this error message is a little truncated / cut off because, again, brand new slide framework that just happened in the last week. But it says cannot borrow v as mutable because it is also borrowed as immutable at v.pushWorld. Note, the previous borrow of v occurs here. The immutable borrow prevents subsequent moves or mutable borrows of v until the borrow ends. Let x equals v or 0. Whew. It's a big long error message. And if you're not familiar with the terminology, it's a little opaque. Once you are, it's super great, and we're working on error messages. A patch I'm actually working on is going to include a URL for every error in the compiler that points to a web page with extended descriptions, sample code, that like this is what this code probably looks like, here's how you'd fix it, and all that kind of stuff. So I'm psyched about that, but we're not there yet. So basically, the issue is because this needs to do the exact same thing as the C++ does. It needs to allocate the second element of the array and then move all the things. But if it does that, it knows that this reference will be invalid. So the compiler at compile time is able to do this kind of analysis and determine that the pointer at x would be a dangling pointer. And so therefore, it just does not let us compile this program without fixing this kind of like ownership issue. And so it's basically telling us what the problem was in the C++ code, admittedly with a little bit of lingo, but it's saying like, hey, you're already taking a reference here. You can't mutate this because we might reallocate, basically. And so this is the example of like how Rust improves this kind of safety. The language semantics have these additional things in them, and I'm going to sort of hand wave what those things all are. But basically what it boils down to is Rust knows at compile time what stuff is pointing to where, and it's able to tell you if you're about to do something that is going to blow things up. There's like an old joke that like C++ isn't just a rocket launcher, but it's a rocket launcher that's pre-pointed at your feet. And so we try to handle this at compile time stuff. I also want to point out that this analysis is done entirely at compile time. So if you can manage to fix this, and I'll show you one way to fix it in a moment, it will compile down to the same assembly code that the C++ will use. Rust actually uses LLVM as a backend, so we get to take advantage of all the performance improvements that happen in LLVM. So this is a compile time cost, not a runtime cost. So this is what I mean by you get the low-level speed of the language while being a little higher level because you get that sort of super optimized output. So here's one way to fix it. And this basically does what the Ruby does. So all I've added is a .clone onto the end of this reference. And so now instead of pointing into the vector, we make a copy of the data that's at the first element of the vector and then point at that. And so now our pointer is not pointing at the place where it would become invalidated. Rust knows everything is OK. And this will compile and it will print out hello. In this particular case, we're now allocating an extra string where maybe we didn't want to allocate that. And there's if this is not an arbitrary example, there are other things you can do that don't involve allocating more memory, but I don't want to do anything. Yes?
If that second push were done in a function, the compiler wouldn't be able to flag the error.
It actually is. It does the analysis through other function calls and stuff. So it would know that you are taking a reference to it there. I don't want to tempt the live coding gods right now, but if we get to the end, I'll show you how that works after we get to after Yehuda's thing just happened. I'm a little skeptical. I don't know if you are in the last talk here, but Yehuda decided to try a demo that involved the network, and that's just always a bad decision. But he tried valiantly. I feel really bad. Okay, so here's maybe this will also give you a little bit of an idea. So here's a much more complicated example, and this involves concurrency. So one of the things that's really cool about Rust is that lots and lots of things in the language are actually moved out to libraries rather than being in the language itself. And it just happens that the language type system primitives work really, really well. So this is spinning up a thread. It's entirely, this is not, I just want to emphasize, I guess, that this falls out of the language semantics. You could build your own threading primitives if you wanted to, and they would have the same safety guarantees because it's not that Rust has special knowledge of threading. It's that the emergent properties of the type system fix problems that happen to be threading problems too. Okay, so this example, let mute numbers equals a vec with 3 integers in them. Right now, I have to annotate those with I. This is an issue that is sort of being fixed. We originally inferred integers to a standard machine-sized integer, but then one of the things that would happen is that you don't know if you compile your code on a 64-bit machine and a 32-bit machine, you have different sized integers, which means you may have an overflow bug that you didn't on another machine, and that sucks. So we took it out and we told everyone to annotate every literal. The problem is then when you put these examples on slides, now I have to annotate the literals, and now I have to explain to you that in real code, type inference would infer this to a sized integer because you have a function that would say something, and it's a mess. So we're talking about adding it back in. I'll talk about stability a little later. And how that works. So for right now, just trust me, this is not the way that you don't normally have to annotate things, but in this example you do. Okay, so for I in range, so Rust does not have a C-style for loop. It uses iterators for everything, and I will talk more about that later, but basically this is an iterator, and it goes from 0 to 3. Spawn is a function that spins up you give it a closure, and it spins up a new thread and runs that code in the closure, basically. And proc is a thing that makes a closure. That is also eventually changing, but it's fine. It will be basically the same thing. You just won't write proc. And then inside that thread, what we're doing is we're calling another range 0 to 3, and we're incrementing these numbers that are in the array. So the closure is capturing the mutable reference to this numbers that's outside of the closure. If you've done stuff like this in other programming languages, you know how closures work. And so this will be mutating inside of a loop with multiple threads spinning up. So we have a whole bunch of stuff mutating an array. And if you've ever dealt with multi-threaded code, you know that this is very bad. I could run this a bunch of different times, and I would get a bunch of different outputs, right? Well, Rust actually knows that this is bad, and it will give you a compile time error. This is actually one of the grosser errors, but happens. So capture of moved value numbers. So note numbers moved into the closure environment because it has some type stuff, blah, blah, blah. So basically, Rust is saying, hey, you already used a reference to numbers in one thread. When you start spinning up a second thread, this is going to be bad news, so don't do that. And so this is really cool. We have this compile time checking of data race. Not technically a race condition because that's a little broader of a definition, but whatever. It's basically a race condition where we'd have multiple threads mutating something at once. Now, that's all fun and good, and if you were using a higher level language, then you might say make a new copy of this array for everything, and you'd be wanting to mutate separate arrays. But sometimes you do need mutable shared state memory between threads, either for performance reasons or because that's how you want to write your code. And if you would be able to wrap this in a mutex, then it would be thread safe, and we would not have that kind of two things updating the same value at one time. So Rust's type system is actually strong enough to be able to encode this in the type system. So this is a long example here, and it sort of gets cut off because of the indentation. So what I'm going to do is I'm going to chop it up into two parts: the part outside the closure and the part inside the closure. So here's the big gross code. Okay, so let's make it a little bit smaller. So here, instead of just doing the vec, we wrap the vec in a mutex, and then we wrap the mutex in an arc. So if you're familiar with mutexes, basically this is a concurrency primitive that will only allow one thing to modify the vector at any given time. So we acquire a lock on the mutex, and then we have to release the lock when we're done, and only one thread can acquire a lock at once. That's the basic idea of a mutex. And then an arc stands for atomically reference counted value. So we need to know when we're able to free this memory. And so since we're going to be accessing it from multiple threads, we don't want one thread to end and then be like, oh, I'm done with this reference, and then deallocate the memory, because that causes a dangling pointer problem. So we want to have this reference count where we're going to count and increment a counter every time we make a new thread. And we want it to be an atomically reference counted pointer because we want to use atomic intrinsics because multi-threading shenanigans. But this works just like arcs if you're familiar with Swift, as I mentioned before, or Objective-C. Okay, so now that we've wrapped the vec in these two things, we can actually do this the right way. So inside here, instead of just making a reference to numbers, inside the loop, I'm going to call numbers.clone, and I'm going to introduce a new variable, number. And what clone is going to do, since clone is on the arc, that's going to bump the reference count up one, basically. And it gives me this new reference to this thing. So it says there's one reference outstanding, and then a second one, and then a third one. And then we spin up our closure. Inside that closure, you notice I have number.lock, so that's the reference to the reference count that I just bumped up. And lock acquires the lock from the mutex, and when it's successful, this will basically block until the mutex is open, and then return the value inside the mutex. So now I have this mutable reference to the array, and there's some dereferencing shenanigans that needs to happen, but basically, if I dereference the value, I can add 1 to that particular position and print out that this element of the numbers is whatever. Now, because of this ownership knowledge, Rust is actually able to then release the lock. You'll notice I don't have a call to unrelease the lock. Basically, because the lock is valid for as long as this array reference is valid, Rust actually at compile time is able to say, oh, this is when array goes out of bounds, I'll release the lock for you then. That way you can't possibly screw up giving up the lock because the language handles it for you. And the same way with the reference count. You'll notice here at the bottom we don't do a decrement on the reference count at all. It knows when that reference goes out of scope, and then it bumps the reference down then. So the type system is able to encode these properties about these concurrency aspects, and it's able to not only only let us share things when we've promised that we've shared them in a way that is okay to share, but we've also managed to not screw up the ability to screw up either the counts or the locking, unlocking mechanism, because the type system is able to handle that for us. Okay, so that's that, and we'll talk. Okay, why not? Demo God's time. I want to talk a little teeny bit more about this ownership thing. All right, since tab. Cool. Okay, so we have a sandbox at play.rustlang.org. Let me see if this actually gets bigger. Yeah, cool. So this actually lets you run Rust code on the web, so you don't need a compiler installed, which is pretty cool. And it's usually only a day or two out of date. So I want to show you one more example of how this sort of memory stuff for this releasing works. I'm going to show you some C code and some Rust code. So let x equals box5. Oh, I'm so bad at typing. It's terrible. Int main stuff. I'm not going to type all that out because that's useless. Int star x equals int star malloc size of int asterisk x equals 5, free x. Okay, so I mentioned that Ruby is safe because it has a garbage collector, and that C++ is not safe, it does not have a garbage collector, right? So Rust has this interesting situation going on where Rust does not have a garbage collector, but it feels like you do, because it does this compile time analysis to determine where the mallocs and free should occur, and it does the right thing for you. So you don't have to worry about the details of the calls. So for example, box is the way that you do a heap allocation, basically. And so this is allocating a pointer to a 5 allocated on the heap. Obviously, allocating an integer on the heap is kind of silly, but like I don't want to get distracted with all the other things that are in here. And then we just like never free that memory. So what Rust is able to do is it's able to say at compile time, okay, you want to allocate an integer on the heap, so I know I need to malloc a size of 1 int. And if this was an array, it would count the elements of the array and it would malloc that much memory. And then when x goes out of scope at the end of the function, I know I can insert a free here. So this is what the code actually is generated by the Rust compiler, is the assembly code that is equivalent to this. But you don't have to worry about this shenanigans or like making sure that you have the right size. We can like look at the type and determine what size it should be, and this stuff all works. As far as like, so the one comment was like, well, what about going across functions? So let me add 1 to this number. We'll add 1, and this is going to take an x, which is going to be a reference to an integer, and it's going to return a new integer. Plus 1. So and I think this is actually going to yell at me, but we'll see how it goes. That's the fun of doing demos.
Do you need a semicolon after you're incrementing?
I don't actually. I don't. I'll explain that in a second. It's a weird thing. I was hoping nobody would ask me about the semicolon, but oh well. All right, let's see. I think this is going to break because it's going to complain. Yeah, so I actually need to pass a reference. This is a little gross at the moment because we don't do automatic. Okay, so we get a 6. So what happens here is I make my 5 on the heap, and then I dereference that value to point into it, and I pass a reference to what it is pointing to. We basically took out all of the like automatic make the references work pretty because we wanted you to like control that kind of stuff. It's still a little controversial because ampersand star is a little gross. But the point is this ampersand int, so this is a borrowing operator. So x is the one that is responsible for freeing this memory, but we only pass a reference to that freed memory, and Rust ensures that there is only one possible mutable reference or any number of immutable references at a given time. And so this is single threaded, so it wouldn't really cause a problem, but like for the duration of this function call, Rust knows that this function is temporarily asking to see an immutable reference to this value, and so it's able to do this kind of like analysis to figure out that it should not be destructed. So like if we were doing threading stuff too, while this was going on, if this like took a while, it would not let anything happen until after it's done. And so this ends up generating the same call in the sense that we don't allocate a new integer, we just pass a reference to it, but we're able to do the type stuff like that. This is the most complicated and most important concept in Rust, and I've written 3 drafts of the guide on explaining this, and I've not been happy with any of them. So I know this is a little confusing, and this is like a talk, and so it probably takes half an hour to totally wrap your head around the way that all this stuff works. So I apologize that I'm not yet better at explaining it. Yes.
Now, in C++, where this would really bite me is not necessarily where I do it like this,
Right.
but where I do it with a function pointer and I select the function at runtime.
Yeah.
So do you do function pointers in Rust at all?
Yeah, so the way that we do function pointers is I could actually, so I always forget the type signature for accepting something, but let's just say function pointer. Let's say that we want x to be a function pointer. I can actually use just the bare name, and it will then turn that into the right function pointer and pass it along, and it's able to handle all that stuff. You still get all the benefits of this type checking because this function pointer signature that is complicated and I forget encodes that information about what it takes and all that kind of stuff.
So any function that match that signature would have to pass through.
Yeah, it does that whole analysis and like figures out that everything's right. Yep. The other thing, I guess I should say, and change this back. I guess it doesn't really matter that much. Yeah, I don't know what I was gonna say there. Never mind. Yay, demos. Okay, so let me get back to the actual stuff. I think it's here. Yeah, full screen. Who knows? Okay, so accessibility. I just threw a ton of code at you with some relatively complicated concepts and explained them only halfway. So maybe by saying this makes it easy for people is like the wrong transition in this particular talk. But I think one of the things that's important is that systems programming, like the systems programming that I learned as a little kid, like I wrote makefiles as a little kid, and today if I was writing a C program, I would use makefiles. Like it's the same, and that's nice because it's familiar and I know makefiles and I love/hate makefiles, but like technology has been significantly improved since makefiles, basically. And so that's cool, and again, stability is really important, but it also means that it's really hard to convince someone that they should be using makefiles today if they haven't been using makefiles for the last like 20 years, because makefiles are a pain. And so systems programming in some ways has been like stuck in this like late 80s, early 90s, not only like mindset, but also like approach to almost everything. And one of the things we try to do very seriously in Rust is use more modern tooling, and it's heavily inspired by so Yehuda also does a bunch of Rust stuff, and so we've been bringing the like Ruby JavaScript mindset to this kind of tooling. So I want to show you one of the tools, which was written by Yehuda, called Cargo, that's like sort of the official Rust package manager / build tool that would like replace makefiles. So it's called Cargo because Rust calls the unit that you compile a crate, and so you ship crates because they're cargo. So there's a little bit of punny stuff there. Cargo.io is taken by some startup, so it has to be crates.io for the website because they're like bankrupt or whatever, but they still own the domain name. Thanks, startups. Okay, so to start a new project, you can do cargo new hello world, and we want this to be a binary, not a library, so we pass the bin flag, and then if we cd into that hello world and we do tree dot, we see that it's set up this very minimal project structure. So we don't need, if you're building a web app, you start doing like models and views and controllers and all this crap all over the place. If you used a tool like Bundler or NPM, you would get all these files. We don't need anything that complicated for this kind of thing, so we have a source folder with our source code in it, and we have a cargo.toml file. You may be wondering what TOML is. TOML is a file format named after Tom Preston Warner, one of the co-founders of GitHub. And basically, it's like INI, but actually standardized instead of just being random and with some extra nice features on top. We argued forever, as you might imagine, with the way the bike sheds work about what file format this should be. And the problem is that YAML is just like totally terrible. I mean, it's fun to use until it like destroys everything due to security vulnerabilities. JSON is a terrible format for human editing configuration because you need trailing commas, or you can't have trailing commas rather, and there's no comments inside of JSON, so it's really awkward, and it's not really human writable in any appreciable way. INI is just like totally a mess because some INI things do this and some INI things do that. It's like CSV, like everyone has their own definition. So we sort of settled on like TOML is kind of okay, but it's like the least terrible option. Okay, and then a source main.rs file. Inside that TOML file, we have these, so this directive package, and then we have 3 keys, hello world version 0.0.1, and then this will actually take from your Git string, it will fill in your name and email address. And those 3 lines are all we need to be able to have this metadata about our project, and inside that main.rs file, there's just the regular old hello world that does this. And so then we can type cargo run, and it will actually compile the project entirely and then run the output, and we get a hello world. So this is really nice in the simple case, but of course, everyone can demo the simple case. What happens when you get to more complicated things? So one of the things that's really nice and why I think that Cargo is a super big advantage over makefiles is this dependency management. So let's say that we want to do versioning stuff, so we're going to import a semver library to handle semver stuff. So we add these 2 lines onto the end of our manifest. So we say dependencies.semver. So this says for the semver dependency, basically, there is a Git repo. So the website for the package manager is up like any couple days or weeks now. So right now you have to fetch everything off GitHub, but eventually you'll be able to just say fetch this from the central repository, please. And there's a whole bunch of other options about fetching a particular commit and tag and all that crap. But for right now you point it at a Git repository, and then what happens is when you write cargo run, it'll say updating Git repository, it'll go fetch that, it'll place it in the right place, it will then compile that library at that version, and you also notice that there's a hash here, so it's actually at a specific hash. I'll talk about that in a second, and then it compiles the hello world thing, it links them all together, and then runs it. So we sort of get this kind of whole dependency resolution shenanigans basically just declarative, you name what it is. This actually then writes out a cargo.lock file that writes out all of the very specific versions. So if then you copy this onto your machine and say that I, as the maintainer of Semver, push up a new commit that would break the world, you'll build with this exact same commit that I've highlighted as opposed to the brand new one that's off of head. And then when you want to update to head, you can run cargo update Semver, and it will fetch the latest version of head and like figure it out. If we had multiple dependencies and they had version restrictions on them, so if, say, I was using some other library that depended on Semver 1.0 or whatever, Cargo will automatically figure out those transitive dependencies and all the versions that are appropriate for all those things and download and put them in the right place and do all the magic necessary and do all the linking flags and all that kind of crap. So it's super, super wonderful compared to like, let me write a make file where I do git submodules and like hope that I'm not breaking everything and like all that kind of stuff. And it feels very familiar to me as a Rubyist, and so therefore it is not scary. The last thing that's really interesting we've been able to do with Rust, this filter call ended up being a little off to the side, but in Rust, we use iterators very heavily, and Rust bets on its iterator support for speed. And what's really cool about like modern compiler technology is this sort of looks like what you would write in Ruby or JavaScript, but it ends up being as fast as a C for loop implementation. So here I'm writing an iterator. So x's is an array. I say x's is going to be a vec of int. So if you want to add type annotations, you'll notice there's been a lot of inference of this overall, but you can actually annotate specifically what you want this to be. And so I take x's and I make an iterator out of it, and I call map, where I pass in an x and I add 1. Then I have a filter where I just do a modulo 2 and test if it's equal to 0, so we get the evens. And then we collect up that list into a final array, and x's will be this vector of integer numbers. LLVM is actually smart enough to realize that these closures can be inlined, and then because these iterators are like stream, they don't allocate intermediate arrays at all. It then does stream fusion and is able to like make both of these things happen on one thing, and so this ends up being like hyper performance, super low level stuff, but you get to write this really nice high level feeling thing. And so this is kind of what I mean when I say Rust is like simultaneously high level and super low level, and that you don't, we call them zero cost abstractions. They're not always zero cost, but they're at least as minimal cost as possible in that we want to give you this high level feel, but we don't want you to have to pay the costs that are traditionally associated with the high level feel. And so that's really an important principle of Rust. Okay, so I'm a teeny little bit early, but so if anybody has any more questions, I'd be happy to go over them, and we'll see about demo shenanigans. Yeah, what's up?
One question about compiler time.
Yes.
In the world of Go, and another question about libraries.
Yes. Third one, before your question, I forgot to mention the stability thing. So Rust is still pre 1.0. But we have told basically everyone that 1.0 will ship by the end of the year, so it's going to have to happen. And it will happen no matter how many nights and weekends I need to work to make it happen, because I've been on stages telling people this, and I don't want to break that promise. What's nice is we are following the Firefox/Chrome/Ember release process. So 1.0 will come out roughly at the end of the year. We have a release candidate at the end of the year, maybe the first week of January. And then 6 weeks later, 1.1 will come out, and it will be a backwards compatible version with some new features. And then 6 weeks after that, 1.2 will come out with backwards compatibly with new features. And so we're hoping that a super fast release cycle like this will enable us to ship stuff really quickly. And it also has really nice benefits for like making the language nicer. So one of the weird things that happens, and I've seen this in Ruby world, when you have a release cycle that's like every Christmas, if someone comes up with a new feature in November, oftentimes you get a half-baked feature shipped at Christmas, right? Because you don't want to have to wait another year to get that feature. So when you have this 6-week release cycle, you can afford to say, like, we're going to put this in behind a feature gate. It's going to show up in the nightly builds, but it's not going to show up in the stable builds. People that want to play around with a new feature and try it out can do it in nightlies. And then if it's the next 6-week point when it makes sense, it'll get shipped. So I think that has good effects for code quality too. But yeah, right now there's still some stuff that is changing a little bit. The core language semantics are totally fine and perfect. It's like we're going over the standard libraries and making sure that similar things are named the same, for example, because we like had no convention for naming stuff and it was built by random people over 6 years. So like there's a lot of really ugly method names that we're just like changing to be nice and consistent and stuff like that. So that's sort of the process we're in right now. Okay, so libraries, and the other thing was compiler speed. So the Rust compiler, first of all, it's kind of notorious for compiling itself is very slow. A full rebuild fresh takes like an hour to compile itself. The reason is that Rust is written in Rust itself, and so it needs to bootstrap, so it actually ends up compiling itself 3 times. And if you do a full build, sometimes we have custom patches that haven't made it into LLVM trunk yet, so sometimes you have to do a full LLVM build and then do 3 Rust builds, and so the compiler itself takes a while. But once you have compiled the compiler, or if you install a binary version of the compiler, it is faster than C++, although not quite as fast as Go. And most of that is due to LLVM, not us. We lean on LLVM's like performance passes quite a bit, and so we've made it as fast as we possibly can, and it is something that we care about, but it is not going to be as fast as Go is, which is one of the big super strong strength points of Go. But it's like, I saw, so someone did a 7-point blog series about writing like a ray tracer in Rust, and they ported their C++ version over, and it was something like the C++ version compiled in like 25 seconds, and the Rust one was like 5 seconds or something. So preliminary reports are looking pretty good. We'll see once 1.0 ships and more people start actually using the language, like how that actually works out, but it is something that we care about. Library ecosystem. So even though we don't have the central package repository up yet, there's a surprising number of packages that do exist. We have like 3 competing web frameworks already, actually, which is kind of interesting. Like a lot of them are sort of more of the like Express/Sinatra kind of thing, rather than like a full Rails kind of deal. But it's sort of interesting, and people are making new ones all the time. There's also weird blind spots. So like we have a really awesome Postgres and a really awesome Redis adapter, but like other databases, I don't know. And so this is what happens when you're in a pre-release ecosystem. But after we got Cargo built, like packages have started to proliferate, and once the central repository is up, things are like, if you graph the curve of packages that we know about, it is like super exponential, which is always going to happen in a nascent community, right? So it is currently being filled out. There are some things that have really, really good coverage, and other things that have terrible coverage, you know, just like everything else. But a lot of people, since Rust has been changing stuff sometimes on a daily basis, I'm actually changing. I'm working on a patch right now that is like literally going to break every Rust program ever, but it's replacing the word fail with panic. So when you fail like a thread, we called it fail and Go called it panic, and we think that name is better, so we're gonna use it too. So that's like a find and replace operation, but it's technically a breaking change, right? So a lot of people have sort of said, this sounds really awesome, Steve, but I am not going to dig into actually learning it until you have some sort of semblance of stability. But a lot of people are like really interested. So the post 1.0, I am like, excited and slightly scared to like be on IRC like January 1st or like whatever this actually ships, and then just watch like tons of people pour in and like have all these questions, and like January's gonna be terrible / awesome. I'm really excited about it. But yeah, so we'll see library stuff continue to grow after that is already then. We have 2 production deployments that we know about. One is OpenDNS. They use it as middleware to do spam catching stuff. So they like connect to ZeroMQ and do shenanigans. The other one is Skylight, Tilde's project that does Rails performance monitoring. The Ruby gem that you install in your Rails application is actually implemented in Rust. And this is one of the areas where like Rust actually shines, is embedding in other languages. Because it does not have a garbage collector, it is trivial to embed in a garbage collected language because you don't have 2 GCs fighting over who owns what memory. I guess I shouldn't say trivial. I should say way more trivial than embedding a GC language in another GC language. And so that's been sort of a niche that's surprising that we didn't really think about at first. Mozilla's motivation, I should have mentioned this too, is writing servo. So the reason that Mozilla cares about this low-level stuff is basically Firefox is implemented in C++, and Firefox, I shouldn't say this, but I'll say it because whatever, it's like riddled with security holes. Pwn to own, like every browser gets totally wrecked, right? There's always security vulnerabilities. And so in the last Pwn to own competition, the 4 security vulnerabilities that Firefox had would have been compile time errors in Rust. Which is a super awesome, significant savings. And so they're actually, the Rust compiler is written in Rust, and then they're writing Servo, which is like a Gecko / WebKit replacement in Rust that I was going to show you my slides in, but I'm not using my computer. And so that's that's Mozilla's motivation, is like browsers need to be high performance and they need to be super safe. So that's sort of why they started building language in the first place. Yes.
What part of C++ you don't support, like templates, dynamic casting, and things like that?
Yeah, so the biggest part in terms of, the question was like, what parts of C++ do we not support, or like what features does C++ have that we don't? The biggest one, so templates is, Rust has a macro system that is hygienic and it operates on ASTs, so it's not like a textual substitution like C's stuff is, but it's a little more restrictive than C++ templates. So we don't have like const expressor and like those kinds of things, although we're like hoping to add that kind of stuff. One of the other things is that like a lot of times, if you are one of those people that wants to do super low-level hero mode kind of stuff, you can do it in Rust, but we have a thing that basically is like unsafe mode that in a block of code turns off some of these safety checks if you're basically making a promise to the compiler that it's okay. And it's a little more, even though you can do the same kinds of things, it's a little more awkward and takes a little more work. So like C++ is better at being dangerous than we are, which is like good and also bad, right? But those are definitely, the other big thing, this is more of a D thing than a C++ thing, but like compile time function evaluation is something that we just don't have that a lot of people like would really like to have, but you can't have everything. So we'll get there someday, but not right now. I would say those are probably the biggest things. The other one is just the ecosystem, right? You can't beat 30 years of compilers and tools and tooling. We can steal some of it with using LLVM, because we share. All those people that Apple are paying to like make Clang better are like also making us better. But you know, like the ecosystem of a pre-release programming language to one that's been around 30 years is like hard to beat. So that's the big things. Yes.
I guess you just touched on this, very briefly. So does Rust interoperate at all with like existing C++?
Yeah. So the question is, what about interop with C++? C interop via FFI is super fantastic. We went to great pains to make sure that it has like zero cost. So for one example, we used to use segmented stacks and we abandoned those because doing that with C is like terrible. And so you basically have like an FFI where you declare like the equivalent of the header files and you just link against it and it just works. We also have a tool that will generate those link header file things for you, and it's mostly awesome. There's occasionally you need to clean some stuff up, but it like gets you most of the way there. C++, we have no real interoperability with, but if it exposes a C ABI, then we interop with that basically. So that's on the author of the C++ library. D has some limited amount of like interacting with C++, but since this is no stable ABI, that's like really hard to do. So we just like do the same thing and we're like expose C please, and we'll handle it. But yeah, FFI is super cheap and pretty easy. I actually, was doing some of that Ruby embedded in Rust, and technically I have a Ruby gem that's written in C, and the C calls into a Rust library, actually, which is like interesting. So you can expose Rust libraries to C as well as like call into C libraries from Rust. So like C int is a different type than R int, and you have to like cast where appropriate and stuff like that. And it is by default unsafe. It has that unsafe blocker around it, so you have to like tell the compiler like I promise that this is correct, and I'm handling some of the details. But yeah, the nice thing about I mentioned a little bit briefly this unsafe mode. Basically, the deal is like if regular safe Rust cannot segfault. So if it segfaults, it's because you have an unsafe thing somewhere that you screwed up. So you only have to audit like this little tiny chunk of code. Cargo actually has zero unsafe code in it at all, entirely. So it's completely feasible to build large programs that are fast without needing to use unsafe. But if you want to bind to a C library or whatever, you can, and then you just know that like that's what caused the problem. Anybody else other stuff? I got, actually maybe I don't know if I have any time. Dude, nobody, okay. Yeah. One more question, cool. I was like, nobody's kicking me off this stage, and then here he is. Yeah, what's up? Yes. Yeah. So what we do is it's very similar to npm shrink wrap, basically. So what happens is if the two libraries are semver compatible, then we only have one version of that library, and we make them do that stuff. So I should have repeated the question. The question is transitive dependencies. If my library A depends on B and C, and B depends on D version 1, and C depends on D version 2, what happens? We can actually, if they're not compatible, like in that example, one's version 1, version 2, it will compile the two different versions and link them against those libraries, and you will basically get duplicated stuff, so it works. If they're like 1.1 and 1.2, then we'll compile version 1.1 or 1.2, whatever works. We'll also do some deduplication if it makes sense within the rules of semver, and if not, then we basically throw an error saying like, hey, there's a problem with, this depends on this depends on that. You got to figure out what's going on. Yeah, it's a good question, though. OK, thanks so much. And feel free to come talk to me the rest of the conference about this stuff if you're interested. Thanks.